A unified kingdom was formed in 3150 before Christ by King Menes, leading to a series of dynasties that ruled Egypt for the next 3 millennia. Egyptian culture flourished during this long period and remained distinctively Egyptian in its religion, arts, language, and customs. They conceived the first number system in history. In addition, they used a number system to store their knowledge. The Egyptians were also the first people to develop a numerical notation. Egypt, country located in northeastern corner of Africa. Egypt's heartland, the Nile River, Valley, and Delta, was the home of one of the principal civilizations of the ancient Middle East, and like Mesopotamia farther east, was the site of one of the world's earliest urban and literate societies. One of the reasons for the overall stability of Egyptian culture was that it was largely isolated by virtue of its geography, with high cliffs and expansive deserts bordering the east and west, the sea at the north, and a series of huge rapids in the Nile to the south, known as cataracts. The stretch of the river valley that gave rise to dynastic Egypt was quite closed off from the outside. Egypt was undoubtedly the gift of the Nile, as the Greek historian Herodotus famously wrote. The influence of this river on Egyptian culture and development cannot be overstated without its presence. The civilization would have been entirely different. The Nile provided not only a constant source of life-giving water, but created the fertile lands that fed the growth of this unique culture. Each year, fed by melting snow in the far-off headlands deep in Africa, the Nile overflowed its banks in an annual flood that covered the ground with rich, black silt and produced incredibly fertile fields. The Egyptians referred to this area as Kemet, the Black Lands, and contrasted its dense, dark soil against the desert, the Red Lands, of the Ethereal Desert. The line between these zones was a literal line. The visual effect is stark, appearing almost artificial in its precision. The annual inundation of the Nile was also a reliable and measurable cycle that held from their concept of the passage of time. In fact, the calendar we use today in the West is derived from one developed by the ancient Egyptians. They divided the year into 3 seasons: Akhet, inundation; Peret, growing or emergence; and Shim, harvest. Each season was divided into 4 30-day months. Although this annual cycle, paired with the daily solar cycle that is so evident in the desert, led to a powerful drive to see the universe in terms of cyclical time. This idea existed simultaneously with the reality of linear time. These two concepts, the cyclical and the linear, came to be associated with 2 of their primary deities: Osiris, the eternal lord of the dead, and Ra, the sun god who was reborn with each dawn. The early Egyptians settled along the fertile Nile Valley as early as about 6000 before Common Era, and they began to record the patterns of lunar phases and the seasons, both for agricultural and religious seasons. By 3000 before Christ, the Egyptians had already developed their hieroglyphic writing. This marks the beginning of the Old Kingdom period, during which the pyramids were built. Hieroglyphs were called by the Egyptians the words of God, and unlike the simple elegance of modern writing systems, this early attempt at recording words used a number of techniques to convey meaning. It is thought that the Egyptians introduced the earliest fully developed base 10 numeration system at least as early as 2700 before Common Era. The written Egyptian numbers were called hieroglyphic numbers. Egyptians had a decimal system using 7 different symbols. 1 is shown by a single stroke. 10 is shown by a drawing of a hovel for cotton. 100 is represented by a coil of rope. 1,000 a drawing of a lotus plant. 10,000 is represented by a finger. 100,000 a tadpole or frog, 1 billion figure of God with arms raised above his head. There are also a written Egyptian numbers called hieroglyphic fractions. All ancient Egyptian fractions, with the exception of 2/3, are unit fractions, that is fractions with numerator 1. For example, 1/2, 1/7, 1/30.
The Great Pyramid of Giza are perhaps the most famous and discussed structures in history. These massive monuments were unsurpassed in height for thousands of years after their construction and continue to amaze and enthrall us with their overwhelming mass and seemingly impossible perfection. Their exacting orientation and mind-boggling construction has elicited many theories about their origins, including unsupported suggestions that they had extraterrestrial impetus. However, by examining the several hundred years prior to their emergence on the Giza Plateau, it becomes clear that these incredible structures were the result of many experiments, some more successful than others, and represent an apogee in line with the development of Royal Mortuary Complex. The three primary pyramids on the Giza Plateau were built over the span of 3 generations by the rulers Khufu, Khafre, and Menkaure. Each pyramid was part of the Royal Mortuary Complex that also included a temple at its base and a long stone causeway, some nearly 1 kilometer in length, leading east from the plateau to a valley temple on the edge of the floodplain. In addition to these major structures, several smaller pyramids belonging to the queens are arranged as satellites. A large cemetery of smaller tombs, known as mastabas, Arabic for bench in the reference to their shape, flat roof, rectangular, and with the sloping sides, that fills the area to the east and west of the Pyramid of Khufu. These were arranged in a grid-like pattern and constructed for the prominent members of the court. Being buried near to the Paroa was a great honor and helped ensure a prized place in the afterlife. The shape of the pyramid was a solar reference, perhaps intended as a solidified version of the rays of the sun. Texts talk about the sun rays as a ramp of the Paroa mounts to climb to the sky. The earliest pyramids, such as the step pyramid of Djoser at Saqqara, were actually designed as the staircase. The pyramid was also clearly connected to the sacred Benben stone, an icon to the primeval mound that was considered the place of initial creation. The pyramid was viewed as a place of regeneration for the deceased ruler. They used the Pythagorean theorem, trigonometry, and simple algebra. They also measured the angle of each direction so that each side of the pyramid was facing exactly north, south, east, and west. Ancient Egyptian mathematics was a vital part of the life in ancient Egypt. The Moscow Mathematical Papyrus is an ancient Egyptian mathematics, also called the Golonishir Mathematical Papyrus, dated to the 13th dynasty, 1803 to 1649 BC, and based on an older material probably dating to 12th dynasty. It is older but smaller than the Rhine Papyrus. The Moscow Papyrus is approximately 5.5 meters or 18 feet long and varies between 3.8 and 7.6 centimeters, or 1.5 and 3 inches wide. The Moscow Mathematical Papyrus is divided into 25 problems with solutions. The problems are organized in no particular order, and the solutions feature much less detail than those in the Rhine Papyrus. The Moscow Papyrus is well known for its geometry problems. Problems 10 and 14 compute the surface area and the volume of the prostrum respectively. The remaining problems deal with the common subjects. Problems 2 and 3 are related to ship's parts. Most of the problems are algebraic Pepsu problems. A Pepsu measures the strength of the beer made from a hecat of grain. And the other one is the Rhine Mathematical Papyrus, one of the best-known examples of Egyptian mathematics, named after Alexander Henry Rhine, the Scottish antiquarian who purchased the papyrus in 1858 in Luxor. It was apparently found during illegal excavations in or near the Ramesseum, dated to around 1550 BC. It contains 84 different calculations to help with the various aspects of Egyptian life, such as building a pyramid or determining the amount of grain needed to fatten a goose. The first part of Rhind Papyrus consists of references tables and the collection of 21 arithmetic and 20 algebraic problems. The problem starts out with the simple fractional expressions, followed by conflation problems and more involved linear equations. The second part of the Rhind Papyrus, being problems 41 to 59 and 59 and 60, consists of geometry problems. Problems 41 to 46 show how to find the volume of both cylindrical and rectangular granaries. Problem 47 is a table with fractional quantities which represent the 10 situations where the physical volume quantity of 100 quadruple hegats is divided by each of the multiples of 10 from 10 to 100.